All right, hi guys, this is worksheet 7. We're talking about magnetic flux, Faraday's law, Lenz's law, and EMF here. So the first thing is with magnetic flux. So with this equation, B is constant. We can tell this is a dot product because we have that cosine theta, where that theta is the angle between B and the normal vector of A. So the normal vector of A, it's like, how does an area have a loop? How does an area have a vector? It's just the normal vector, which means it's coming like straight out of it. So most of the time that angle is 0, and we know that's pretty helpful because cosine 0 is equal to 1. So you got to like ignore that here. Again, that's a dot product. Faraday's law, within Faraday's law, this tells us that a charge in a change in magnetic flux results in an induced current, right? So in what ways can we change the flux? There's a few different ways. We can change the magnetic field strength. So that's that B variable, right? We can increase it, decrease it, what have you. Another way you can alter B is by altering the current, right? We talked about how like the current will have a B field at certain areas, with like the right-hand rule number 2. You can also change the area encompassing the magnetic flux, or you can change the orientation of the loop between 0 and 90 degrees, right? So if it's like standing straight up, you can just like put it on an angle and that counts. Next is Lenz's law. So Lenz's law is kind of confusing to like determine the direction of the induced current. So I have a trick to do that. I'm going to go through each one kind of stepwise here. So there's 4 different scenarios of how this will behave. I'm going to start with scenario 1. The first one is you can increase the B field going into the loop. I'm going to say loop, but it could be like a square or whatever, right? Like a square loop. But anyway, you can increase the amount of B field going in. So by Lenz's law, you're going to want to oppose that. So you need to increase the amount going out. When you want to have more out, that tells you it's a counterclockwise induced current. The next option is you have less B field going in to the loop. So through Lenz's law, you want to have more going in. That in tells you clockwise induced current. The third scenario is you have more B field coming out of the loop. And by Lenz's law, you want to have more going into the loop. Again, in, that tells you clockwise. And finally, when you have less B field coming out, by Lenz's law, you want to have more B field. You want to have increased B field going out. So that's a counterclockwise induced current. So those 4 scenarios basically highlight every single way in which it can exist. I know there's like a few different ways to do it. Just pick what you're comfortable with. Either use that list, use whatever you want, and go from there. Okay. So this EMF equation number 4, we use this when we're increasing or decreasing magnetic flux in the shape of a square or rectangle, right? And these B, L, and V must be mutually perpendicular. So what do I mean by that is like you'll have your B field pointing up. You'll have L kind of, like on its side like this. And the velocity is going to be going like straight that way. So there's going to be 90 degrees between all of them. And the last one is in regard to AC circuits, right? So here we have this RLC circuit, like summary of equations. And I'll show you, it's intimidating because there's a bunch of them, but it's really just like plug in a bunch of equations and solve all the way through. And truthfully, it's actually like pretty easy. The only thing I want to recognize is like impedance here. That's effectively the total resistance of the circuit, right? And then the phase angle, I always solve using tan, right? You can also solve it using cosine, but the tan way of solving is actually more informative as it tells you how the current behaves relative to the voltage, right? So when your phase angle is greater than 0, that tells you your current is actually lagging behind the voltage. So effectively, like your current will reach its max before the voltage can. And inversely, when your phase angle is less than 0, the current leads ahead of the voltage. And the current reaches, for the first one, it reaches Imax after the voltage. And then, because it's lagging behind, right? And in the second scenario, it leads ahead, so it reaches Imax before Vmax is reached, okay? And then we have average power equation where the RMS is equal to max over √2, and that can apply to a bunch of different RMS values. So this one is not something that he went over in lecture, but it is normally a big part of AC. So I just included the equations here. If it's something we don't need to know, we won't cover it again, but I just want to have it someplace, and I'll ask him if these are relevant. And if not, we'll just forget about it and keep going. Okay, so here, question 1. We have a few different scenarios and we're looking to find the direction of the induced current here. Okay, so for this first one, I'm not going to draw it out because I feel like it'll be easier for us to like all be seeing the same thing here. But I could draw it out if people on Zoom think that'd be helpful. But let's just try me explaining it here. So we have the current going upwards and that current is increasing. So what does that tell you about B? B is also going to be getting bigger, right? So you put your right hand rule number 2, right? You put your thumb in the direction of current, you curl your fingers. You'll see that on the left side, so on this side of the wire, we have the B field coming out of the page. So in this situation, when we have more coming, so we have I increasing, so we have more coming out of the loop. We have increased B field coming out. By Lenz's law, we need to have more going in. In tells us clockwise. Therefore, your induced current here is clockwise. Now, let's look at scenario B. So with B, we have this magnet moving closer towards this loop. Okay. So how does the magnetic field come out of a magnet? It comes out of the north side, coming out like this, right? Shooting around like that. It's coming out like that. As it gets closer, again, we're having more coming out of the loop. And therefore, to oppose that by Lenz's law, we need to increase the amount coming into the loop because we're going to have an increased amount coming in, therefore, clockwise induced current. Now, looking at letter C here, we have now a loop moving away from the south terminal of a battery. So the B field is coming in and it's like the vectors are coming towards the south terminal. As you move it away, you're going to be having less coming into the loop. Because we're having decreased B field coming into the loop, we need to increase the amount going, by Lenz's law, increase the amount of B field going into the loop. Therefore, per that statement of in, it's going to be a clockwise induced current. Looking at this one, again, this is a right-hand rule. Put our thumb in the direction of the current, fingers curl in. Here we're going into the page. I is getting smaller, so B field's getting smaller. We're reducing the amount going in, and because we're reducing the amount going in, to oppose that by Lenz's law, we need to increase the amount going in. Per that statement of in, clockwise induced current. In scenario E, we have this loop. This loop enters a region where there's a magnetic field. It continually enters this region. That means more B field is coming out of the page. Because there's an increase coming out, by Lenz's law, we need to have an increase going in to oppose that. Therefore, clockwise induced current. Lastly, this loop now is exiting the B field region. Therefore, we have less coming out of the page. Decreased B field coming out, we need to increase the amount coming out. Therefore, through the statement of out, counterclockwise induced current. So yeah, this is one of the concepts that is better shown in person. So I don't know how helpful this will be, but I hope that you can pause and listen to the explanation. So basically they're all clockwise except for F. I'm going to pause the recording and take any questions. All right. So now question 2. So here we have a square loop as shown in the figure here. And it is placed in a magnetic field that decreases at this rate per unit time. The resistance per unit length of the wire is this. So this is the resistance per unit length. This is all, whenever it's like something per time or something per unit length, it becomes confusing. So let's be very clear here. You know what I mean? This is over time, this is over some distance. We want to first determine the EMF, and then we also want to determine the magnitude and direction of the induced current. So let's start with part 2 here. I'm going to stop the share. All right, does this look? Yeah, this looks good. So let's start by writing what we know. This is question number 2 here. Okay. So we know that there is some change in B over some amount of T, right? So there's a change in B over a change in time, right? And that is, they give us as 0.03 t per second, right? We're told it decreases. Therefore, what is the sign right here? Minus. It is decreasing, therefore minus. It's kind of small. We'll write bigger for these next ones. Now, we're also given the resistance per unit length. I like to represent that as a unique variable because I know that I'm going to need to solve for the actual resistance to solve for the induced current. So I'm going to call this mu. I'm going to call it mu. 0.3 ohms per meter. All right. So in part A here, part A, we're going to use the Faraday's law, right? This is a change in B. It's decreasing. So E induced, right, part A here, E induced is equal to minus N delta I over delta T. What is N equal to? Anybody on Zoom know what N is equal to?
Coils.
I heard someone say something. I didn't hear what they said though, but it's 1. Ow. Just walked into this. I heard. It's equal to 1. There's 1 loop. Okay. So, we can just pop that guy out. We're left with minus V over delta T. Nice. Okay. And we know we can now plug in. This is equal to BA cosine theta. And what's the angle between B and A? In this case, it's 0, right? We have like the loop flat. So that means the A normal vector points straight up. And then coincidentally, what's the B vector? It's also coming straight up too. So the angle between them 0, cosine 0 is equal to 1. So we can just replace this with minus delta B A over delta T. Okay. So now this part takes some intuition here. What is this delta sign? What does this delta sign tell us? What do we use that for? It tells us a change, right? So a change in time, a change in area, whatever. In this situation, is the loop getting bigger, staying the same, or becoming smaller? It's staying the same. What about the B field? The B field is changing. So therefore, the delta only applies to the B, right? So delta B, we can pull that area out. There's no change in A over delta T. Okay. At this point, we can just plug in for area, where area is equal to the sides squared. So minus, we're going to call it S squared, and then delta B over delta T. Delta B over delta T, we already know that. So, the sides here, what were they? 0.03 squared times delta B over delta T, which was 0.03, minus 0.03, I should say. These minus signs cancel out, and what you get is 0.0000, that's 4 zeros, to 7 volts. Right? All right. Cool. Okay, so kind of like the important thing to recognize here is, normal vector comes straight out of the area. It's equal to 0 most of the time. What's changing here? The area is not changing, but the B field's changing. And you can kind of see how those negative signs canceled out, which is sweet. And then in part 2, we're asked for I induced. So how do we get I induced? Well, we need to do that through Ohm's law. Sorry, I have a bad chalk right now. So V equals IR. Or as applied in these scenarios, it's that induced EMF, the I induced times the total resistance. Okay? But what do we know? We know induced EMF. We don't know I induced. That's what we're solving for. And we don't know R total. But what we do know is the resistance per unit length. So if we take that mu, that's equal to the total resistance divided by the total length, right? So now we can make a adjustment to solve for the to solve for our total. We'll call that, let's see here. Did I rename it? Yeah, I'll just say this. Let's say our total is equal to mu times 4s. Okay, so that's this value mu times the total length, and there's 4 sides of length s. So now I can rearrange this equation to induced EMF divided by R total, where I showed you what R total is equal to, which equals I induced. You're going to plug everything in, and what you end up with is I induced equal to 0.3075 amps. Okay. Now we're almost done here. We got the magnitude, but we need to state the direction. So in this scenario, we have B field coming out of the page, right? It's decreasing. So per that fact, we're having less coming out of the page. We're having a reduced amount of B field coming out of the page. To work through Lenz's law, right, to like effectively oppose that, we need to have more B field coming out, because that second statement we said out, therefore it's a counterclockwise induced current. All right, let's take questions on this one. Okay, so now in question number 3, I'm gonna make I'm not going to do part 2 of this question because it might address something that we're not going to go over. I was going through the slides and I noticed he made no reference to it. So I'm going to skip that for now. If it does become, I'm going to follow up with him. If it becomes relevant, we'll make sure to discuss it down the road. But it is kind of like a more complicated, I mean, just as complicated as everything else, but no point to add something unnecessary here. Okay, so here we have a conducting rod with mass M that slides down 2 conducting rods, as shown in the figure. We want to determine the direction of the induced current. Okay, so, oh, this is going to be kind of quick right here. So we have this rod going down where the field's going in. So effectively what's happening is that loop is expanding, right? It's becoming bigger. Because of that, there's more field going into the page there. So through Lenz's law, we need to increase the amount coming out. So therefore, it's going to be counterclockwise there. Okay. So part A, we'll move on to question 4 now. I don't want to address like a point that's unnecessary. Okay, so here we have an LRC circuit, and we have the resistance, capacitance. It's an AC source. They give us the frequency and the Vmax right there, right? So the first thing we want to do is determine the total impedance. That's that Z value. So to solve for Z, we need to also find XL and XC, like by definition of the equation. So this is equal to 2 pi FL, where all this stuff is given, and this is given equal to 1 over 2 pi FC. Okay, you plug everything in. This guy is equal to 39.8 ohms, and up here is equal to 56.6 ohms. Okay. So now we have enough to solve for Z because they gave us R. So that's going to be R squared plus XL minus XC squared. Plug everything in. Z comes out to be equal to 200.7 ohms. Okay. And you're going to see like this is a very like stepwise process. You just got to start with, solving for Z and then just keep working it along. In part B, we're asked to solve for Imax, where Imax is going to be equal to Vmax over Rmax. Again, both of these things are given. They sometimes call it like V naught or like I naught. That's equal to Imax. But to me, like it's easier to just call it Imax so you remember it's the max, Anyway, so Imax equals 0.24 amps. Okay, that's part B. The next one is part C. We're asked to find the peak voltage across all of the circuit elements, right? Across each one of them. So we have RLC, right? And you need Imax to do this. And that's because we'll say the Vmax of the resistor is equal to Imax times R. And it's basically the same, plug in what we just saw for down here. R is given, and you can kind of repeat the same process for each one. So Vmax Vmax L is equal to Imax XL. Okay, and this guy is equal to 13.6 volts. Vmax C is equal to Imax XC. Okay, equal to 9.6 volts. Okay, so that's each one. Now in part D, we want to find that phase angle between the voltage and the current. I like to use tan here. So D tan phi is equal to XL minus XC divided by R. Inverse tan, plug everything in. This angle comes out to be equal to 4.8 degrees. Okay. And finally, in part 5, I should say, we're asked to determine the average power dissipated in this circuit. So here we're just going to use the P average equation. Okay. So P average, or P average, there's many equations. In this case, let's use IRMS squared times big R. And we remember that everything RMS is equal to that, it can be VRMS or it can be IRMS, whatever, is equal to whatever that variable is, in this case, I max divided by √2. And therefore, to find I max, it's just the RMS times √2. Okay. So we can just rewrite this. Geez, it's like brainstorm. I max over √2, this whole thing squared, times R. I max we already solved for, just divide by √2, and then the R is given. All this comes out to be 5.76 watts. I want to say this, don't be deceived with how easy this one is, because when we're asked to, starting with impedance, and then find I max, and then this next part, and then part D, and then part E, it's very clear to be solving each one. But if they told you to just find P average, given the starting stuff, it's going to be kind of hard. So I'm going to remind you to be tipped off to start with impedance. Work to find I max, because you need I max to find each of the circuit element behaviors. Phase angle, that's dependent on XL and XC, and same thing with P average, it's dependent on I max. You'll see that I'll never ask you to solve for XL or XC or report those, because that's normally represented in the impedance, it's represented in the phase angle, it's represented in the voltage max across each element. So yeah, it's easy when it's told to you stepwise, but remembering the process is kind of the point of this question. So I recommend you do it like this. And like I said, so for question 3 and question 4, I'm going to follow up with him. If it's relevant, I'll let you know and we'll see it again. If it's not relevant, I'll let you know and you won't see it again. Okay. So I'm going to stop the recording here. And yeah, thanks for watching.